Hello everyone, and welcome to the newest course by Project Polymath, Introduction to Higher Mathematics, Math 150. I'm very excited to be teaching this course, and I look forward to sharing the beauty and awesomeness of mathematics with all of you. First of all, let me introduce myself. My name is Bill Shillito, and I live in Marietta, Georgia. Like some of you taking this course or watching these videos, I consider myself an aspiring polymath. I've never been satisfied with dedicating my life to just one topic, but rather have always reveled in studying many things and seeing how they're all connected. That being said, math has always been a particular passion of mine because of how it so often seems to link everything together. I graduated from Georgia Tech in 2008 with a Bachelor of Science in International Affairs and Modern Language. I concentrated in Japanese and have traveled to Japan twice so far. I also speak Spanish. In fact, I've always been interested in languages and linguistics, so I've studied the workings of many other languages, from French to Chinese to ancient Egyptian to even Quenya. As for my current profession, I've been teaching and tutoring in math since 2009, and I'm about to pursue my Master of Arts in Teaching so I can teach math at a high school or perhaps university level. I've also been published a couple of times in our local Math Teacher Association's periodical, Reflections. And I'm soon going to have an animated lesson featured on TED Ed, showing a more intuitive way to do matrix multiplication. One other particular interest of mine that's closely related to math is music. I play both piano and viola, and I've been composing music since I was in elementary school. Most recently, I've contributed music to a number of video games. Anyway, enough about me. Let's talk about us and what we're going to be doing in this course. The purpose of this course is to help you build a strong foundation in mathematics. You'll be developing your abstract thinking skills, which will include learning how to write proofs. One thing I'd like to point out is that this course requires absolutely no knowledge of calculus. In fact, some of the topics you encounter here will be quite beneficial to you if you take calculus after this course, because calculus rests upon the foundations that we'll build, especially in the properties of real numbers. In fact, a goal for this course is that the topics we'll talk about and the skills you'll develop will prepare you for more advanced math courses you may take in your future studies. As we progress through this course, we're going to cover a number of topics that serve as some of the underpinnings of mathematics as a whole. Among these topics are logic, set theory, relations and functions, number theory, abstract algebra, cardinality, and real analysis. Note that as this is a 10-week course, we'll only be hitting highlights of certain topics like number theory, abstract algebra, and real analysis. These are very rich topics to which we could devote an entire class. However, while we won't be going too deeply into them, what we will be discussing is why they're important and how they contribute to the cohesiveness of mathematics. We'll also see what we might call the adhesiveness of mathematics, seeing how math applies to topics such as physics, computer science, cryptography, art, and music. These connections will help cultivate a more complete understanding of the topics we'll discuss. Finally, we'll delve a bit into the history of mathematics and meet the unique people who made all of what we're talking about possible. Anyway, without further ado, let's go to our first lecture, Problem Solving 101. So, before we talk about how to solve problems, we have to ask ourselves the question, just what is a problem? Many students believe they know what a problem is in math. They claim they've been doing them all their lives. Well, I can't speak for the rest of the world, but at least in the United States, this is often not the case. In my country, what often masquerades as problems would be better termed exercises. These amount to little more than reading a sentence, usually called a word problem, translating it into arithmetic, doing one or two computations, and arriving at the correct answer. Take a look at this so-called word problem. Johnny goes out with 4 of his friends. They each buy a slice of pizza for $2. How much was the total bill? This word problem is nothing more than a contrived way to ask the question, what is 5 times 2? Some may say there's a slight challenge because some students may see the word 4 and think the question they're supposed to do is, what is 4 times 2? But in reality, that's a rather lame attempt at making a question more challenging. However, before I turn this into a rant on the American educational system, let's consider what a problem should be. The National Council of Teachers of Mathematics, or NCTM, sets out guidelines on what it considers worthwhile mathematical tasks. The standards say that math teachers should pose tasks that engage students' intellect, stimulate students to make connections and develop a coherent framework for mathematical reasoning, and are based on knowledge of the range of ways that diverse students learn mathematics. This begins to give us a better idea of what makes a good problem. They should have answers that are not immediately obvious, and there may be more than one valid way to approach them. For example, consider a class learning about area and perimeter. On one hand, an exercise might look like this. Find the area and perimeter of each triangle. This task just requires you to apply the formulas for area and perimeter a couple of times. Not very interesting, is it? On the other hand, a true problem might instead look like this. Suppose you had 64 meters of fence with which you were going to build a pen for your large dog, Bones. What are some different pens you can make if you use all the fencing? What is the pen with the least play space? What is the biggest pen you can make, the one that allows Bones the most play space? Which would be best for running? The questions asked constitute true problems because they ask questions that require investigation, conjecturing, and critical thinking. There are many ways to go about solving such a problem. Think about how you might tackle some of these questions. Good problems should also foster students' ability to reason and communicate mathematically. Mathematics is an ongoing human activity, and as a social species, is one that is often best tackled together. This is why, by the way, I fully encourage you to collaborate with each other for the homework I'll be assigning for this course. Discuss things, reason them out, and don't be afraid to voice your concerns, opinions, and ideas. Anyway, now that we've established what a problem really is, it's time to talk about how to go about solving them. As we've seen, mathematical problems often have many ways to tackle them, but it's useful to study what most effective problem-solving strategies have in common. So, I'm going to introduce to you a problem-solving framework adapted from a book I highly recommend called Thinking Mathematically by Mason, Burton, and Stacy. Don't think of this as a step-by-step process that must be followed to the letter when solving problems, but more of a suggested guideline for how to focus your efforts. The problem-solving process can generally be broken up into 3 parts: an entry phase, an attack phase, and a review phase. No matter how you tend to solve problems, these 3 phases are often present to some varying degree. Let's look at each phase in turn. The first phase is the entry phase. This is the phase entered when you first ponder a problem and prepare to attack it. Some people just try to haphazardly dive right in after reading the question, but this usually ends in frustration. It's important to recognize that the entry phase is a vital part of problem solving and should not be overlooked. In the entry phase, there are 3 questions that you must often consider. What do I know? What do I want? And what can I introduce? First, think about what do I know? This is usually answered from 2 sources. First of all, what do you know from reading the question? Second of all, what do you know from past experience? Often you've encountered exercises or problems, or even real-world situations that involve similar principles to the ones on which your problem is based. The second question is, what do I want? This is where you isolate exactly what you're looking for. In many cases, it helps to write the essentials of the problem in your own words. This helps you ensure that you understand your goal. Always make sure to watch out for possible ambiguities in the question's phrasing, though. Remember, language can be a tricky thing. For example, if my question is talking about a circle, do I care about just the outside edge of the circle? Or do I need to think about the interior of that circle, which is usually called a disk? We often use circle to describe both concepts, but in math, it pays off to be precise. Finally, you should ask, what can I introduce? This often will supplement your rephrasing of a question in one of 2 ways. First of all, in many cases, it helps to make a diagram to help properly visualize the situation. Second of all, it helps to represent the question in a mathematical notation to see what's going on under the hood, and possibly eliminate extraneous details. Now, when I talk about reading the question, I can't emphasize enough, be very careful when reading. It's far too tempting to just try to pluck the numbers out of a question and slap some pluses and minuses between them without really understanding what the problem is asking. For instance, consider the following classic question. How much dirt is there